Hello and welcome to Advanced GCE Mathematics, feedback on June 2015 Unit FP2 live online event. Here are the aims and objectives for this session. In this training session, you will receive feedback on national performance of candidates in Unit FP2 of the June 2015 examination series. Consider the variation of candidates' performance on different questions and possible reasons why. Discuss the examiner's reports. Address common issues and FAQs. Here's the outline that we will be following during this training session. Introductions, delegate polls and agenda. Introduction to the FP2 qualification and feedback on the FP2 June 2015 examination. Common issues. Further training. Any questions? Finish. Now, we're going to start with the introduction to FP2. Here's a screenshot of the specification. Please download it from the website if you think it's necessary. The paper was found to be accessible to a wide range of candidates. The mean score was 58 out of 75. The work was generally well set out, although some handwriting was difficult to read, with some variables being indistinguishable from each other, for example, U, Y and X in question 8. Timing did not appear to be a problem as most candidates seemed to finish the paper. There was some evidence that candidates spent too long on question 3. Some candidates are still attempting to use a formula without quoting it first, for example, the Taylor series in question 7. This question tested inequalities. The most efficient solutions involved either 1. Multiplying through by x plus 3 squared, or 2. Collecting terms to one side and finding a common denominator. Some wasted time with method 1, expanding to obtain a cubic when there was a common factor of x plus 3. The most common error was to multiply through by x plus 3 with no consideration of the effect of the direction of the inequality. The question asked for the use of algebra. Candidates are at liberty to use sketches once they have used algebra to find the critical values. A graph helped to answer Part B. Many candidates just gave their answer to Part B as their answer to Part A. Efficient solutions involved multiplying through by x plus 3 squared, or collecting terms to one side and finding a common denominator. Incorrect solutions involved multiplying through by x plus 3 only. This question tested complex numbers and the application of de Moivre's theorem. Almost all candidates were able to attempt Part A, and the correct modulus was seen in the majority of responses. Virtually all candidates gained a mark for using the correct approach for the argument, but obtaining minus pi over 3 was the most common error. Many candidates could attempt Part B, although a surprising number left the answer unsimplified, as, for example, 4,906 cos 4 pi plus I sine 4 pi. Part C was answered poorly in relation to A and B. The majority of candidates preferred to find z cubed first, and then find the fourth root. A significant proportion applied de Moivre's theorem and were able to find a single root, but a significant proportion only found one further root and so did not gain further marks. Many candidates were successful in Part A. In Part B, some candidates did not simplify their answer. In Part C, many candidates stopped after finding one route. This question tested finding the solution of a first-order differential equation. The first 3 marks were obtained by many candidates using an appropriate method. The most common error here was obtaining the integrating factor as cos x. To integrate the RHS, good candidates spotted that using cos 2 theta equals 2 cos squared theta minus 1 gave an integrable function and obtained the required solution quickly and efficiently. Some correctly integrated by parts once and then used the cos 2 theta substitution, and a smaller number correctly used a factor formula. A common response was to attempt integration by parts and to give up after one application. Those who didn't give up battled on, usually obtaining an incorrect integral, although many candidates tried several approaches before abandoning their attempt. This question tested knowledge of the method of differences. This question really tested the candidates' mathematical communication skills, and many were let down by poor notation and a lack of reasoning. Most candidates were able to prove the given result in Part A. The majority opted to expand the 2 pairs of brackets first, and then either multiply by r squared or simplify. A small number used the difference of 2 squares. Many candidates did not gain full marks for Part B. Some candidates treated the identity as if it were an equation, and started by dividing throughout by r squared. Most made some attempt to list terms, but some did not list sufficient terms to demonstrate that cancelling would occur. In particular, candidates had a tendency not to write down a complete result for r equals n. In Part A, the majority opted to expand the 2 pairs of brackets, then multiply by r squared and simplify. Many were let down by poor notation and a lack of reasoning, and candidates had a tendency not to write down a complete result for r equals n. The next stage of the process was to extract the terms which had not cancelled out. Most candidates were able to do this correctly, although some did not explicitly state n squared n plus 1 squared, and others wasted time expanding this result, which was not a necessary step. Candidates who had been listing terms without considering the left-hand side of the process often reached this stage and did not know how to continue. Others made mistakes expressing the left-hand side, showing a general uncertainty about how to deal with the quarter. The final step of the proof proved to be the most problematic, as many candidates ended the proof with the sum of the cubes equals the sum of the squares squared and not the given result. This was a question on transformations of the complex plane. Many candidates demonstrated excellent algebraic skills and worked through Part A very well, achieving the full 8 marks. Common errors were forgetting to square either the 2 or the 3 when finding the modulus, and these lost all the subsequent accuracy marks. Some candidates began by using z equals x plus yi and found an expression for w, which they then multiplied by the complex conjugate of their denominator in order to make the denominator real. However, very few got beyond this point, as they were unable to see how to use mod z equals 2 in this context. In Part B, most got the follow-through mark for drawing a circle on an Argand diagram that was correctly placed for their centre and radius. The last mark required the correct circle to have been drawn, so was not accessible to those who had made errors earlier. For the shading, a sensible approach was to use the coordinates of the centre of the circle to find whether it was in the region required. Common errors in Part A were forgetting to square either the 2 or the 3 when finding the modulus, and these lost all the subsequent accuracy marks. This was a question on polar coordinates. This question was very well answered. In both parts of the question, the majority of candidates knew the methods needed to solve the problem and were able to apply them accurately and with good use of mathematical notation. Those who did struggle with Part A were still able to achieve some marks in Part B. In Part A, most candidates were aware that they needed to differentiate r sine theta, but some struggled with solving the resulting quadratic. In Part B, the formula for area was used confidently, and the majority of candidates were able to manipulate r squared into an integrable form using the double angle formula for cosine. The most commonly seen errors in this question were slips, such as evaluating r squared as 3a, 1 plus cos theta squared, or 3a squared, 1 plus cos theta squared, getting a sine wrong in the double angle formulae, or integrating cosine to obtain negative sine. This was a question on the Taylor series. In Part A, the first derivative was achieved correctly by most candidates using the chain rule. For the second derivative, most candidates chose to differentiate the first derivative as it stood rather than to rewrite it solely in terms of tan x first. In Part B, a few candidates gave an expansion in powers of x rather than x minus pi over 3, and some did not expand as far as necessary. The final mark was lost by candidates who otherwise had a perfectly good solution by either writing the answer as f of x equals, where there had been no prior definition of the function f. The omission of root 3 was sometimes seen in the coefficient of x minus pi over 3 cubed. In Part A, the result was achieved correctly by many candidates. In Part C, some candidates incorrectly gave an expansion in powers of x. This question was on second-order differential equations. Part A was a challenging question for many candidates, although some could achieve the result efficiently. The first derivative was usually found quickly, easily, and correctly. It was the second derivative that caused the majority of problems. Almost everyone who attempted the second derivative realized the product rule would be required, but some failed to use the chain rule as well, and then struggled to make further progress. There was evidence of many candidates adjusting their previously incorrect working, scribbling out, overwriting, and squeezing in extra variables to try to get the given result. Candidates generally did considerably better with Part B. A few candidates derived the auxiliary equation rather than simply writing it down, but most examples of this were completely correct. Forming and solving the auxiliary equation was dealt with confidently, and the vast majority achieved m equals 4, and then produced an acceptable expression for the complementary function, which usually appeared in factorized form, although occasionally as two separate terms. When attempting the particular integral, most candidates knew what was involved and started with an appropriate linear expression, although there were several examples of careless algebra and calculation errors, which meant that the correct coefficients could not be obtained. A typical error would be starting with y equals au plus b, getting to 16a equals 2, and stating that a equals 8. A more serious error was candidates' use of y equals au or other equivalent linear expressions without constant terms. This was seen far too often. Candidates were familiar with the need to combine their complementary function and particular integral to obtain a general solution, and therefore many received the mark here. A more serious error was candidates' use of y equals au or other equivalent linear expressions without constant terms. This slide shows the distribution of marks on FP2. Candidates should make sure that they state formulae before attempting to use them. Candidates should be very careful in the presentation of their work and make their variables clear. Candidates should be aware when they are spending too long on a question when they could be scoring marks on other questions. Candidates can also return to a question later if they have time.